All right. Coming back to little statistics, I'm going to finalize some probability. So we're going to go into counting. So another way that we analyze probability is by understanding different outcomes that can be considered. So counting is a method we use to calculate all possible outcomes in specific events. So I'm going to go ahead and look at the multiplication counting rule. Okay, and the multiplication counting rule is right here. I look at the sequential events and I look at those outcomes and I have to multiply them together and it'll figure out what it is. So let's look at an example. In how many ways can I create a 3-letter password? So here, in just this question here, we must analyze the logic that represents this. So in creating a 3-letter password, 3 letters means I'm looking at the alphabet, which has 26 letters, and a 3-letter password does allow for replacement. So that means that I can take those 26 letters and repeat them, and so I'm using this multiplication counting rule. So 26 times 26 times 26 is 17,576, which means there are 7,576 different ways that I can create a 3-letter password. Okay. There's also a factorial rule. So basic concept of factorials, and with the exclamation point right there, implies that I am able to create a product of all whole value digits that are descending from the value that it starts all the way down to 1. So, for example, 5 factorial simplifies to 5 times 4 times 3 times 2 times 1, which is 20 times 6, which gives me, so 5 factorial is, let me see, 5 factorial gives me 120. Okay, so that is that rule right here. So if I consider a 3-letter password with non-repeating letters in it, that means whatever letter I used in the first one can no longer be considered in the second one. So that's why it went from 26 letters to 25 letters down to 24 letters. So then if I choose to create a 3-letter password but with non-repeating conditions, my choice is reduced now to 15,560. Okay, so let's see here. In how many different ways can I rearrange the word COVID, right? So this means rearrange means that letter can only be used exactly only once. So this means without replacement. So without replacement means I have to use that multiplication rule, and my sample space going to each different sequential event is reduced by 1. So it does have that factorial rule into it. So in how many ways can I rearrange the word COVID? 120 ways, yeah? How many different ways can I rearrange the letters in the word day? So there's 3 letters in the word day. 3 times 2 times 1, and I'm showcasing it here. So here's 1, 2, 3, 4, 5, 6. So these are the 6 ways, which proves the rule is valid. Okay, moving on. Now we're going to look at combinations. So combinations and permutations. Combinations look like this. This is the format. And permutations are like that. So they have the same little format, but they do differ by 1 tiny little factorial, okay? So let's look at combinations. Order does not matter here. So that means, remember my little scenario where I showed you the different ways that I can rearrange day? These are all considered isolated events because those are different ways. So here, order does matter. So they are considered differently. But when order doesn't matter, all of these would be considered the same outcome. And so here, is what I'm showcasing. DAY is equivalent to DO. These would be considered the same one because I'm still using the same letters, okay? So here's the formula. And the formula for combinations is n factorial divided by the difference between n and r. So n is the amount of items available to choose from, and r is the amount of items being chosen. So the formula says n factorial over the difference of n minus r in a factorial with additional r factorial on the denominator, okay? So again, remember, order does not matter, which means order free, okay? So let's just say we're looking at a lottery that picks 3 daily numbers out of a total of 56 numbers that are available. And order doesn't matter. As long as you get any of these 3 numbers that are chosen, you're able to win the lotto. So again, there's 56 numbers and 3 are chosen. Order does not matter. So I'm plugging it into my formula. Here's my formula. You know me, I always like to start with the formula. Now I know n is 56 and r is 3, so it gets applied into the formula. 56 factorial divided by 56 minus 3 factorial times 3 factorial. So notice there's a difference, but then the r factorial is still there. Order of operations says 56 minus 3, because that's parentheses, must be simplified first. 56 minus 3 is 53. So I have 56 factorial divided by 53 factorial times 3 factorial. So I'm going to explain this little situation with a little simplified version. Let's say I have something like this. 7 factorial, and then I have 7 minus 2 factorial and 2 factorial here like this, okay? So if I have that, notice that this is going to become 7 factorial over 5 factorial and 2 factorial, okay? So I could easily do this. 7 times 6 times 5 times 4 times 3 times 2 times 1 all over 5 times 4 times 3 times 2 times 1 times 2 times 1. By doing that, that means this 5 cancels with that 5. This 4 cancels with this 4. This 3, this 3, this 2, this 2, this 2, 1, like that, yeah? So I'm left with 42 over 2, which gives me 21, okay? Now watch what I'm going to do. I'm going to go ahead and I'm going to problem the way I'm going to showcase it in the example that I'm going to follow. 7 factorial divided by 7 minus 2 factorial times 2 factorial gives me 7 factorial over 5 factorial times 2 factorial. Now, I recognize that this is already a factorial, and that factorial is present here. Notice, 5, 4, 3, 2, 1. So I'm able to rewrite 7 factorial as 7 times 6 times the factorial of 5. So that's exactly what I'm going to do. I'm going to say 7 times 6, and the rest are really the factorial of 5. So then this is going to be 5 factorial and 2 factorial. Now that I have that, I can easily just cancel that. And now I have 7 times 6 over 2 times 1. And that gives me 42 over 2, which equals 21. So you are more than welcome to go ahead and do this. But sometimes in analysis, your factorials are not going to be relatively small numbers. So I would recommend understanding this scenario here so you can understand what I'm doing. So that's exactly what I did here. So I have 56 divided by 56 factorial divided by 53 factorial times 3 factorial, which means I went 56, 55, 54, 53 factorial divided by 53 times 3 factorial. So the factorials cancel out. I'm left with 56, 55, 54 on the top as factors divided by 3, 2, 1. This is equivalent to 166,320 divided by 6, which is 27,720. So from 56 numbers, choosing 3, there's 27,720 different combinations you can do. And if you just buy one lotto ticket, your probability of winning that is this number right here, which converts into a 0.00361%. So that's a very unlikely situation. Let's look at permutations now. So combinations, order doesn't matter. But now permutations, order does matter. So this would be two different outcomes when in the other one it wasn't. So let's look at the formula here. My formula is NPR is equal to n factorial divided by n minus r factorial. So let's notice that formula for NPR is n factorial divided by n minus r factorial, and the formula for combinations is n factorial divided by n minus r factorial with an additional factorial. So let's talk about what this does. This one, order matters, which means I'm going to have way more different combinations. Here, order doesn't matter. Like the word day, those were 6 different combinations here, but in this situation, it was just 1. So that r factorial on the bottom, it's like when I took it over here, I can do, let's just look at it. If I have 3 letters and I choose, I don't know, one to look at day, here, this divider here is going to give me 1. And this one over here is still going to give me that 6 because this guy is going to make it a smaller number when my dividing number is going to be smaller. So let's look at it again. N is equal to different items available for selection, and R is the number of items being chosen. So here, notice, permutations is only the difference. There's no R here. So again, let's look. California Lottery uses 56 numbers. Daily 3 is a game that selects 3 non-repeating numbers. How many different selections can there be? So 1, 2, 3, and 3, 2, 1 are 2 different methods, and you have to, in this particular example, order does matter. So 1, 2, 3, and 3, 2, 1 are not equivalent. So if my winning numbers are 1, 2, 3, and your ticket is 3, 2, 1, you didn't win. You had to get the 1, 2, 3. Okay. So again, how many numbers are there in the total pot? 56. How many do you need to get to win? You got to get those 3 in a specific order. So again, here's my formula. Plugging in those values, I get the following. 56 divided by 53. This is 56, 55, 54, 53 factorial divided by 53 factorial. Bam, bam, that cancels. I am left with 166,320. So again, probability of winning is 1 out of 166,320. So the odds are pretty low. Okay? Let's look at another one. And here, I'm going to be looking at the differences between scenarios where I need to determine, am I using permutations or am I using combinations, okay? So if I have 15 students trying out and the coach needed to select the starting team in basketball. So does order matter here? Order must matter here if you are selecting for specific roles, like point guard, forward, short guard, center, etc. So order does matter here. So then it does gonna have to give me permutations. So permutations, that means out of 15, I'm choosing 5. So plug in my formula. Remember, permutations is only n factorial divided by n minus r factorial. So 15 factorial divided by 15 minus 5 factorial is equal to, right here, notice, 15, 14, 13, 12, 11, 10 factorial divided by 10 factorial. These cancel out, but notice that whenever I have here, I am left with a 1. That's my identity element of multiplication. And I'm going to showcase this example here. When I have 4 divided by 2, this means I broke down this 4 to 2 times 2, and this 2, I broke it down to 2 times 1. Some people just write it as 2, and they just go, oh, yeah, this 1 is still there. It's the identity element of multiplication, and that justifies why there's a 1 here. So how many different combinations of a starting team using 15 students for a 5-team basketball startup do I have? 360,360 different combinations, okay? Now let's look at this one. What if my kids were trying to start a volunteer panel of 7? So now here, that 7 is not does not require a specific role. You just make a panel. So order does not matter. This is Mauricio, this is for my college students. This is statistics, babe. You should be looking at my Algebra 2 classes. Okay? These are for my college students, for my statistics kids. I do have mercy on you. So 15 kids tried out of the school, volunteered for a panel of 7. Here, there's no role. So order does not matter. If I choose 1, 2, 3, 4, 5, 6, 7, and 7, 6, 5, 4, 3, 2, 1 in that order, those are the same. It would be the same panel. So this is where the combination rule comes into play. So NCR is equivalent to n factorial divided by n minus r factorial times r factorial. So again, how many people am I choosing? 7 out of how many? 15. Plugging it in, I have 15 factorial divided by 15 minus 7 factorial times 7 factorial. This equivalates to 15 factorial over 8 factorial and 7 factorial. Again, I'm going to use that factorial simplification little hack that I showed previously, which meant 15, 14, 13, 12, 11, 10, 9, 8 factorial divided by 8 factorial and 7 factorial. Now here, you could have just put in a 15 factorial divided by a 8 factorial and 7 factorial on your calculator. But if you wanted to do this manually, I'm going to showcase this so you could see. I have 15 factorial over 8 factorial and 7 factorial. Okay, so I recognize that I have 15, 14, 13, 12, 11, 10, 9. I'm going to leave the rest of it in the factorial of 8 divided by 8 factorial and 7 factorial. Notice that the 8 factorials cancel. So I'm left with 15, 14, 13, 12, 11, 10, 9 all over. And I'm going to open up the factorial of 7, 7, 6, 5, 4, 3, 2, 1. Now let's look at this. I recognize that 6 times 2 gives me 12. So do you see how 6 times 2 on the bottom is 12 and the top on the 12 canceled out? That's one. Let me do another one. I also recognize that 15 and 5 times 3 cancel out. Okay. And then let me do another color. I recognize that 14 divided by 7, there's a 7 that I can cancel out here, but I'm left with a 2 there. And I'm also recognizing that I have, I think that's it. So I have 2, 13, 2, 13, 11, 10, 9 divided by 6, 4, and 1. If you want to further simplify that, now you can plug that into the calculator, or you can further simplify that as I can say that I can factor out a 2. So this and this leaves me a 2 here, 10, and a 5 here. Notice I factor out a 2 there. And then I can also factor out this 2 and this 2 now. And then now I have 9 and 6. I can factor out a 3. So this is going to be 3 times 2. It's going to leave me a 2 and a 3 here. And I think that's it, because now these are, so I have 13, 11, 5, and 3 over 2. So let's see what I get. 13, 11, 5, and 3. So that gives me 6,435. As you can see here, again, if I want to calculate using the calculator, let me show you. Where's my factorial? Okay. So if I want to use 15 factorial, so I'm going to go 15, and then I'm going to go to math, probability, and number 4 is my factorial. So notice that I added that right there, right? So I'm going to go ahead and put that in. Let me put that in parentheses so you can see it. So again, math, probability, And option number 4 is my exclamation point divided by, and I'm going to put parentheses like that, 8 factorial and 7 factorial. And that gives me 6,435, which is right there. So what does this mean? If out of 15 kids I need to make a panel of 7, I have 6,435 different ways to do that. So now let's talk about the binomial probability distribution. So this is where, let me get a new blank page so I don't confuse you with that. Okay. This is an analysis of probabilities that only have 2 outcomes. So you have a sample and you ask a specific question that you either have a yes/no marker to. Like, for example, I'm serving 250 college students. I want to know, are you here for transfer? Or are you here for an AA? So if you're here for transfer, that's going to mark yes. If you're here for an AA, that's going to mark no. So binomial means I only have 2 possible outcomes, a yes or a no situation. Some of these markers can be as heads or tails if you're, flipping a coin, success, failure, winner, loser, or yes, no. Okay. So some requirements for a binomial probability is that there has to be a fixed number of trials. Trials must be independent. That means the probability of any particular trial is not affected by previous nor future trials. And the binomial, the probability of success is equivalent on all of them. So this all contributes to this independency that they have. Okay, next one. Let's look at the notation. For binomial probability analysis, I have probabilities of successes. So that's what this P of S means. And the probability is denoted by lowercase p. Probabilities of failures is denoted by lowercase q. And in your entire distribution, the sum of probabilities of failures and the probabilities of successes must equal 1 because they are complements of each other, which means if I know the probability of my success, then I'm able to then figure out the probability of my failure by looking at the difference they have within 1. Because since it's a one or the other situation, you're looking at a binomial analysis of a complement. And again, here it means the number of fixed trials that you're analyzing, and X is the number of successes that you're trying to calculate the probability for. Okay. So this right here is the binomial probability formula. If you notice, it looks relatively similar to another formula we have. Where did I leave that, Pepper? Right here. Let's see if we can look at that formula real quick. Notice that P of X is equal to n factorial divided by n minus x factorial times x factorial. That looks very similar to this formula right here. So you understand that the binomial probability analysis has some type of combination analysis aspect onto it with a multiplication rule analysis with the probability of successes and the probability of failures, okay? And so here we go. Let's look at this. I have, again, X is the number of successes. So if I'm trying to see, like, out of a trial of 10 people, what's the probability of 3 of them being successes? So that would be P of 3. The N would be the 10. Probability of success, if we recognize the probability of somebody saying yes to a particular question was like an 80%, that means the probability of failure would be 20%. My P and Q must be expressed within the formula as decimals. So when I look at this, I say when an LATTC student is randomly selected with replacement, there is a 79% probability that they are studying a trade. So here, the question is yes, no. Are you studying a trade? Yes or no? Success would be if they answered yes to the question. Fail would be if they answered no to that question. What is the probability that exactly 3 of 5 LATT students are studying a trade? This tells me 79% that they are is my P. So that's going to be expressed as a decimal, P of 79, okay? And that means if I know that the probability of success is 79%, then I know the probability of fail is 21% because these must add up to 1. So lowercase p is 0.79, lowercase q is 0.21. Now, my trials, there's 5 trials on there. I want to know what's the probability of me choosing exactly 3 that answered yes. X is the number of successes. So, again, here's my formula. It looks intimidating. It really isn't. As long as you recognize what the problem is giving you for givens, plug in your givens. 5 factorial divided by 5 minus 3 factorial times 3 factorial times my probability of success rate, 0.79 to the third power, because that's the x, and 0.21, that's my q, to the 5 minus 3. So this simplifies to wherever there was a simplifying part, I have to simplify. 5 minus 3 becomes 2 factorial. So 5 factorial divided by 2 factorial times 3 factorial is 0.79 to the third power times 0.21 to the second power. So again, come over and I simplify this. I break down my 5 factorial to 5, 4, and 3 factorial, and then 2 factorial and 3 factorial, my 3 factorials cancel. 5 times 4 is 20, divided by 2 is 10. 0.79 times 3, to the third power means 0.79 times 0.79 times 0.79. And then 0.21 squared, right there, gives me this particular value. Again, this is the probability in decimal format, but my answer would always require you to answer the question. The probability that exactly 3 out of 5 LATTC students are studying a trade is 21.74%. So I took this number here, converted it back to a percent for the context. Okay, let's look at another one. Here we are. And what is the probability that at least 4 students are studying a trade? So at least something means, so let's analyze first at least 4. At least 4 means, remember, I have 1 trial, 2 trial, 3 trials, 4 trials, 5 trials. At least 4 means 4 or more. What's the most I can have? 5. So the probability of at least 4, it implies that I have to look at the probability of 4 or the probability of 5. Or is addition rule. Now these are independent events, so there's no intersection. So remember, the addition rule is P of A or B is equal to P of A plus P of B minus the intersection of A and B. Now, these are independent events, so there's not going to be any A and B. So it's just going to be the summation of that. So probability of at least 4 is equivalent to probability of choosing 4 or the probability of choosing 5. Okay? So I want to make sure we recognize that because that's how I'm going to look at this problem. So again, we recognize I have a 79% probability of having somebody say yes, they're studying for a trade. That means that's a 21% probability of them saying no. So now here, I got to do this scenario twice. I got to find it for 4, but I also have to find it for 5. So here's for P of 4. Wherever there is an X, I replaced it with a 4, N is still 5, P is still 0.79, Q is still 0.21. Okay, so doing this analysis, I'll leave it there so you can see. I recognize that this is going to give me 0.40898. This is the probability of having exactly 4 out of 5 students saying that they are studying a trade is 40.9%. Now let's look at what is the possibility that all students in the trial, so 5 out of 5, indicate that they're studying a trade. Again, big thing I have to say is that 0 factorial is equivalent to 1. That's a rule. And any any number to the 0 power is also equivalent to 1. You need to understand this because in this problem, my n and my x and my n are the same number. So when I take a difference of them, I'm going to end up with a 0 here, and also here I'm going to end up with a 0. So these rules are essential to understanding the analysis of what is the probability that all trials are successes. So again, here's my formula. Just that, with my plugged in given values. 5 factorials cancel. I'm left with 1 over 0 factorial. 0 factorial is 1, so that gives me 1 over 1, which is 0.79 to the 5th times any number to the 0 power is 1. So this gives me 0.79 to the 5th, which breaks down to this, which is 0.30771. So this breaks down to the possibility or the probability of selecting 5 out of 5 saying that they're studying a trade is 30.77%. So now the possibility of at least 4 means I got to add these two probabilities together, and that's exactly what I did. 0.40898 and 0.30771 right here are added, gives me 0.71669, which indicates that the probability of at least 4 out of 5 students studying a trade is 71.67%. And that is it, folks. Remember, this is for my college students, high school students of mine. This is a college course video. You should be looking at my Algebra 2 videos, and your assignments posted on my website. Enjoy the rest of the day, everybody. Stay safe.